So in this video, we'll be working through a bunch of problems, taking the derivative using the limit definition of the derivative. If you want, you can just skip to exactly the kind of problems that you feel are most appropriate for you. So these problems really take you from just about the easiest type of limit derivatives that you can take to just about as complicated as you can go. And with the skills from these, you can do most basic problems of this type. So let's go ahead and get started with number one. So the first one is just taking the derivative of a constant, of a number. There's nothing special about 3. This works exactly the same for 0 or negative 12 or pi or whatever. So let's go ahead and get started. So remember that the derivative of f is given by the limit as h goes to 0. So this is what we refer to as the limit definition of the derivative. So for this one, we'll really focus on understanding what each part is. And in the later problems, we'll just assume you understand that. So the first thing here is f of x plus h. So that means take the equation f and replace any x's you see with an x plus h. Well, on the right, there are no x's, right? It's just a 3. So there's nothing to replace. It just stays 3. So that makes it pretty easy here. So let's go ahead and do that. So I'll go ahead and plug those in. And if I do that, what we see is f of x plus h is 3. What is f of x? We just look up top. F of x equals 3. And on the bottom, h is just h. Okay, so of course, that just becomes 0 on the top. We get 0 over h. 0 divided by any number is 0. So that gives us 0. Okay, so one thing that I know some people struggle with is right here, normally when you take limits, you want to plug in h equals 0, since h is going to 0. But there are no h's. So actually, that means it's easier. So here, I'm going to look at this, and I'm going to change h to be 0. Well, there's no h's to change, so it just stays 0. So that is, in fact, the derivative of 3. So here, f prime of x equals 0. Okay, so let's go ahead and go on to the next one. So now we're going on to sort of the next level up. So what we'll do is we'll start out exactly the same way. Just to help you out, let's go ahead and write out the whole limit definition of a derivative. So it's f of x plus h minus f of x over h. Okay, so let's compute on the side here what is f of x plus h. So f of x plus h means I take my equation, any x I see, I replace it with x plus h. And I find you can generally do better if you put things in parentheses. You're less likely to make mistakes. Okay, so that's what f of x plus h is. So let's go ahead up here and plug that in. So that becomes 3x plus 3h minus 1 minus f of x. What is f of x? It's 3x minus 1. And our h on the bottom just stays h. Okay, so the next step is really just to simplify this, to kind of clean it up. We've got some like terms on the top. So the first thing I'm going to do is just the negative in front of the parentheses here. I'm going to go ahead and distribute that. That gives me negative 3x and positive 1. And next, we've got some like terms, right? We can see that we've got on the top 3x minus 3x. Those cancel out. And we've got negative 1 plus 1. Those cancel out. So all we're left with is 3h over h. And so here the h's cancel. I get the limit as h goes to 0 of 3. And this should look very familiar to the ones I did on the last problem. So we want to change h to be 0. Well, there's no h there to change, so it just stays 3. So there we go. So to wrap it all up there, we get that the derivative of 3x minus 1 is 3. And there we go. Computed the second one. Okay, let's go on to the third one. So here's where things start to get to be a little bit more work. It's not that they're necessarily harder, it's just that there's more steps involved. So at this point, I'm going to go ahead and assume that I don't need to write the whole limit definition out. Let's just go ahead and do it. So I take f of x plus h. So I take my equation, I change any x's to be x plus h's. So that's what f of x plus h looks like. minus f of x. Again, if you put things in parentheses, you're less likely to make mistakes. and I leave my h on bottom. So again here, what we want is to start simplifying and collecting like terms. So a common trick that shows up a lot is if you've got something that you can square, often you should square it. So up here I've got x plus h squared. If I do that, if I FOIL it all out, I get x squared plus 2xh plus h squared. Okay, so let's go ahead and just keep the rest of the terms. And while we're at it, I'm going to go ahead and distribute that minus sign. So that becomes minus x squared minus x. Now this might not be very fun because you've got so much stuff all over the place. It might feel like, gosh, this is just getting horrible. But the point is, as soon as you write it like that, you'll see that lots of things can cancel out. So I see I've got an x squared and a minus x squared. Those cancel out. I've still got my 2xh here, so let's go ahead and leave that. I've still got my h squared. Let's leave that. Then I've got an x minus x. Those cancel out. So all I've left with at the top now is that h. Then on the bottom, I'll leave my h. So this is good because, remember, the goal is always to plug in h equals 0. But if I just tried to do that right now, I would be dividing by 0. I'd have a 0 on the bottom. But now I see everything has h's in it. So I like to be very careful in my work. I'm going to go ahead and factor out the h on top. So if I do that, that's what I have on top. And then I can cancel out my h's. So if we go ahead and do that, we see what we end up with is the limit as h goes to 0 of 2x plus h plus 1. And now we can just plug in h equals 0. So we do that, and that gets 2x plus 0 plus 1, which is, of course, 2x plus 1. So there we go. So the derivative of x squared plus x is 2x plus 1. So that's a trick you see a lot when taking derivatives using the limit definition of a derivative, is you've got something you can square out, and if you square it, you'll end up being able to cancel lots and lots of terms, and things will look much nicer afterward. So that's definitely something to keep in mind. In fact, I would say that is one of the two main tricks that shows up for taking these derivatives. Okay, so let's go ahead and do number 4. So number 4 is the square root of x. And this is one that looks pretty simple, but it can really give you trouble. And we'll see exactly how you can deal with that, though. So let's just jump right into the limit definition. So we know I first take my equation, I plug in x plus h minus f of x over h. Now, a lot of people get here and they're just stuck because they look and they say, what the heck can I possibly do? I can't subtract those square roots. I can't cancel anything. I can't square anything out. I don't know where to go from here. So this is the second big trick that shows up a lot with taking these sorts of derivatives. So the trick is, what you want to do is you want to multiply the top and bottom by the conjugate of the top. Remember, the conjugate is just a fancy way of saying, take the thing you've got on top and switch the sign in the middle. So we've got a minus in the middle. I switch it to be a plus, but everything else stays the same. And the reason we want to do that is it makes the top turn out much nicer. So let's go ahead and just multiply it out. So if you multiply out the top, you FOIL out the top, what we get is the first two multiply together, and we get root x plus h times root x plus h, which is just x plus h. So that's the first term. Then in the middle, we get a plus root x times root x plus h. And then the next term in the FOILing gives us the opposite of that. And this is really the power of multiplying by the conjugates. You get these two terms in the middle, which are going to cancel. And now we get root x times root x, which is just x. Okay. On the bottom, actually what I'm going to do is I'm not going to multiply it out at all. And if you were the one doing this, you might not know that you shouldn't multiply it out. I mean, it's not going to hurt you to multiply it out, but it'll save you time if you don't. Okay, so let's go to the next step here. We'll see why we're doing this the way we are. So on top, let's see what we get that cancels out. So I have an x that cancels out with a minus x at the back. That's great. I have an h on top. And now I have root x times root x plus h, which cancels with minus root x times root x plus h. So that's it. There's just h on the top, right? And the bottom, now you can kind of see why I did not want to multiply that h on the bottom. because I was going to cancel it at the next step. So if I would have multiplied it in, I would have had to factor it back out. So I'll cancel those h's. I'm left with 1 over root x plus h plus root x. And now I can plug in h equals 0. And if I do that, I get root 1 over x plus 0 plus 1 over root x. That's just 1 over 2 root x. And there we go. We have taken the derivative of the square root of x. So we see that actually this one maybe looks bad at first, but once you do the multiplying, it's actually pretty short. In fact, if you did problem 3 with me, you see this is actually less work than problem 3. Okay, so with that, let's go on and do problem 5. So let's go ahead and start working through this one. So this one really is the third and final trick that you see a lot when working with these derivatives. So the first trick came from problem number 3, where if you can square something out, oftentimes it is helpful to do so. The second trick is multiplying the top and bottom by the conjugates, like we did in problem number 4. So here's our final trick. So let's go ahead and get started. So I plug in x plus h minus f of x over h. So again, when you get here, it may not be obvious what you should do next. And that's why I say this is sort of another trick that shows up. But really, all you do is you have fractions and you're subtracting them. Well, if you have fractions and you're subtracting them, how about you subtract them, right? Get common denominators and subtract them. So let's go ahead and do that. I'll do my scratch work off to the side here. So if I have 1 over x plus h minus 1 over x, my common denominator is going to be x times x plus h. So this one, I multiply top and bottom by x plus h. This one, top and bottom by x. And if I do that, what I get is x over x times x plus h minus x plus h over x times x plus h. Okay, on the top, the x minus x cancels. I'm left with minus h over x times x plus h. So a little messy, but no big deal. Okay, so let's go ahead and put that in on the top. So I'll keep my limit. And then we just saw that the top can be rewritten as negative h over x times x plus h, that whole thing over h. Okay, let's keep going. So the next step is just to clean this up a little bit. And what I want to do is just not have this double fraction. So dividing by h is the same thing as multiplying by 1 over h. So I keep the top of the fraction exactly the same. But instead of dividing by h, I'm going to multiply by 1 over h. And hey, this is great for us because I see h's are going to cancel when I do that. So if I go ahead and cancel those h's, what I'm left with is negative 1 on the top. On the bottom is x times x plus h. So again, now I can plug in h equals 0. I'm not going to be dividing by 0 if I do that. So let's go ahead and do it. I'll plug in h equals 0. I get x times x plus 0, or that's the same thing as negative 1 over x times x. In other words, negative 1 over x squared. And that is indeed the derivative of 1 over x. So I hope that makes sense, and if you have any questions or if there's more topics you'd like me to talk about, please leave a comment in the section below. If you found this video helpful, give me a thumbs up and be sure to subscribe, and I'll see you all again soon.